Now I've rewritten this expression that we will use, and this one as well. So we just in the previous session we just derived these two relations between the Hermite polynomials. Now, if that's true, you can rewrite this hn minus 1 as 1 over, you divide both sides by 2n, so you get this expression, right? So, so I can, now it's true for n, it's a general n, so I can express that a little differently and say h of n minus 2, make your n go down 1, becomes 1 over 2 to the n minus 1, h of n minus 1 dz. Right? So let's find an expression for h n minus 2. So so this is just d by dz of h n minus 1. But we've got that expression, so just plug this in here. Okay? And so this 2n comes outside, so you get 4n into n minus 1 underneath. And so you're differentiating this twice now with respect to z. So you get d squared hn dz squared. Alright, now from this here, we can rewrite, and this is also for general n, so we can rewrite this slightly differently. Instead of n plus 1, we can just have an n, hn. So we'll take this n and take it down 1. So we'll have hn equals 2z n minus 1, okay, minus 2, and the n now has gone down by 1, so it's now 2 to the n minus 1, h to the n minus 2. Alright? Why do that? Because we've got hn minus 1 as a first differential here, and we've got hn minus 2 as a second differential, and that's the sort of thing we want for Hermite's equation, because the Hermite's equation involves a second differential and a first, and the question asks us to use these two expressions here to derive Hermite's equation. So presumably by using these two directly, maybe it'll just drop out, it'll come out nicely. Let's hope so anyway. Right? So rewrite this with n taken down 1. So that will become here. Okay? Alright, now what is hn minus 1? Well, it's this. So put that expression in. There it is here, putting that in. The 2's will cancel. So you're left with z over n, that's here. Now, minus 2n minus 1. Now what is hn minus 2? hn minus 2 is this here. So put that expression for this. Left out a bracket. Okay, so put this in for here. Now the n minus 1's cancel, and you're left with, so this just becomes z over n dhn dz minus 1 over 2n, the 2's cancel, and the second differential. Okay? And so all this then equals hn. Right? So multiply both sides, that's this side and this side, by 2n. So that'll get rid of your coefficient for the second differential, d squared hn dz squared. Okay. So you're multiplying both sides by 2n, n's will cancel, you get a 2z here, or minus 2z hn dhn dz, and equals 2n h equals naught, right? So so just take take these two terms over to the left hand side, and that'll leave 0 on the right hand side, and there it is. And that is your ME's equation. So it dropped out. Now I don't know how obvious or difficult that seemed. I thought amongst the mathy type questions they were a bit more difficult, so I thought I'd do those two. So both ME type questions relating to the simple harmonic oscillator discussion in the physics. Alright, now two physics type questions in connection with a free wave colliding on a barrier. So this first one's not too difficult. So what you've got is you've got a particle coming in, and you're told that its energy is 9 times V0. It doesn't really matter about the units, as you'll see. And then at x equals 0, it hits a barrier, and the potential V is 5 times V0. Okay, 5 times. So the energy, in other words, obviously the energy is greater than the barrier. So there'll be some reflection and some transmission, right? But some of it will continue on because the energy is greater. And you're asked to show that big T, that's the percentage, the fraction of your probability going through your big T, is in fact 96%. So nearly all of it goes through. So you're asked to calculate big T and show that it's 96%. All right. Well, from the theory, we had a formula for. I asked you to calculate this big T for homework, but here's the actual formula. So big T is 4k, little k dashed, divided by the square of the sum of little k plus k dashed. Now, what are these k and k dashed? Well, it's in. Have a look in the theory. These little k's are just used to simplify the Schrodinger equation. So little k by definition was square root of 2me over h bar squared, and k dashed was square root of 2m into e minus v over h bar squared. Okay. Now e in this case is these. you can see that these numbers here have been chosen to make the calculation convenient, right? That's pretty obvious. So e here is just 9v. Okay. Now 9 inside the square root very conveniently. So your k here. So for your e you just put 9v. So you got the square root of 9 is 3. So you take a 3 outside. All right. Now for k dashed, your e is 9v, and your v, the potential here, is 5v0. Oh, sorry, 9v0. 9v0. And this is 5v0. Okay? So 9 minus 5 is 4v0. Very convenient. You can see it's been rigged. So the 4, square root of 4 is 2, so you get a 2 coming out. So your k, little k, is just 3 times this square root. I won't bother saying what's inside. So just 3 times square root blah blah. And k dashed is 2 times square root blah blah. Right? So t, so just we now know what k and k dashed are. So just plug them into this formula for t, and it should come out fairly easily. All right. So big T will the fraction of the probability that goes through. So just plug in these 3 square root and 2 square root. Just plug those in for k and k dashed. So you'll get 4k. So it's 3 times square root. K dashed. Well, that's 2 times square root. And then k plus k dashed all squared. So that's 3 root plus 2 root, which is 5 root all squared. Now you got root and root. Wait a minute. Yeah. So root, you got here 5 roots squared, so it's 25 root squared. Here you got root, so root squared. So the root squared